Hey guys, my name is Adam. I'm a UConn Mentor, and today we'll be going through Big O notation. So what is Big O notation? Big O notation is the notation we use to describe the complexity of an algorithm in terms of input size n. It describes the worst case scenario. Big omega describes the best case, and big theta describes the average case, but we always want to use big O because anything that can go wrong will go wrong. It's used to compare algorithms. And so we have some examples. O of 1 is a constant case. N is equal to 1. So it's always going to be 1, which is pretty nice. We like that. O of n is linear. It's going to increase the more n increases. And O of n squared is like O of n, but now the graph is like this. So it's going to increase much faster. So for example, if we have this algorithm and it wants us to find the third letter, what our program is going to do is it's going to start at D. It's going to go 1, 2, 3, and then it's going to end. It's found the third letter. So that was 3 comparisons. If we have a different input, say Jake, it's also going to go 1, 2, 3. And we can even do it on supercalifragilisticexpialidocious. It doesn't matter. It's just going to compare the first 3 letters and then stop. That's pretty nice. It's a constant time, and it doesn't matter how long the input is. Now, if we try something else, algorithm 2, is there a G in the word? So our input is Dagny. So what it's going to do is it's going to go not G, not G. Yes, that's a G. We can stop now. So it only took 3 comparisons. But say our input was Dabney instead of Dagny. Now, it's going to go not a G, not a G, not a G, not a G, still not a G. And then it's going to end because it has no more inputs to check. That took 5 comparisons. So say our input is now a supercalifragilisticexpialidocious. Now it's going to have to check every single letter in this 33-letter word to make sure there's not a G in there. That's pretty bad. As you can see, it's increasing the longer our n is increasing. So as our input size grows, the number of comparison grows at the same rate using the worst case scenario. Say algorithm 3. So this wants us to find all the common letters. So what it's going to do, it's going to start at G and compare it with J. Not common, not common. But regardless whether it's common or not, it has to check every single letter in the word Jacob. Now, for one letter D, it compared all 5 of Jacob. Now there's 5 letters in Dagny, which means it's going to be 5 times 5, and it's going to be 25 comparisons. So the amount of comparisons that are necessary are rapidly increasing because the exponent of the n increased as well. So we have a graph that shows roughly the efficiency of these algorithms. So O of 1 is actually right along the x-axis. You can't really see it. O of n is right here. It's the green one. And it's going up, but it's not going up too fast. As we get over here, you can see the amount of operations needed to compare an even small amount of elements is really going up really quickly, and that's really bad for us as programmers. So what we have is O of 1 is nice, or it's O of, yeah, it's a constant, not too bad. O log of n is also nice. It's not bad. It keeps the amount of comparisons per size of list pretty low. O of n is O of k. It's not bad, but it's not great either. O of n squared, oh my, it's not very good. Then you have O2 of n, which is, oh no, it's even worse. And then O n factorial is, oh my god, that's the worst possible one you can get. So that's just been a brief overview of algorithms. I hope it helps.